All right, welcome to part 3 of our lecture video series for Monday, April 24th, where we are now going to discuss how our enthalpy equation will be changed as a result of a condition placed on our chemical system such that pressure itself is constant. So let's talk about what this means to be at constant pressure. So typically, when we're in the lab, like when we have looked at chemical systems, we have not looked at a chemical system like the one given up here, where we've got like these closed containers where we perform some reaction inside, but rather we've looked at some kind of, I don't know, aqueous reaction, where maybe we've had some kind of reactant products, reactant materials react and form, I don't know, let's suppose it's a precipitation reaction, form some kind of precipitate solid. So let's think about what makes this particular example of like our standard reaction that's carried out in the lab in an open beaker, one that is at constant pressure. So when we're in the lab, we take great care to try to control as many of our lab condition parameters as possible. Now, I know that you probably think I'm a liar because every time we have stepped into our Chem 210 lab, it's been like boiling hot, right? There's not been a lot of thermal or temperature control in that room, and you are right. However, one thing that is pretty common is, we do not expect for there to be major or significant fluctuations in pressure as we perform our chemical experiments in the lab. Because if these chemical reactions are open to the atmosphere, then in reality, like whatever pressure is being exerted or pushing down on our system, and then thus also, what our system is pushing back up on, is in some equilibrium with one another. Particularly, we say that their pressure is atmospheric pressure. So there's no change in pressure that's going on here because we've reached some kind of pressure equilibrium between our system and surroundings. We're not changing how pressurized the room is. We're not putting our system under vacuum, right? We're just performing things out and open in the air. So we're performing things at lab pressure, which is typically just normal atmospheric pressure at sea level. So how does that affect then something like our internal energy, total internal energy, and then our enthalpy? So just starting out for our chemical system, we have the definition of total internal energy as being the sum of all of our means of energy transfer, here being our heat. So that's our thermal energy transfer as a result of some change in temperature, and work, which is any other means of transferring energy. And in particular, we have said that the heat due to some temperature change or difference plus the work in this particular class has been pressure volume work. So that's pressure external times change in volume. Okay. Now, the volume could certainly change as a result of some chemical reaction, right? I could produce water as a product and change in some small amount of volume as a result of some new liquid being made, right? That's not totally out of the question. So, what's going to happen then with enthalpy? So, enthalpy, recall, is our change in total internal energy plus the change of the product of pressure and volume. And here, the thing that is constant is pressure. So if I were to expand this out, I would get that enthalpy is equal to the change in my total internal energy plus my constant pressure times my change in volume. And if I replace in what I know from my definition of total internal energy as being heat plus work, fully written out like this, then doing a substitution allows me to write that this is mc delta T minus pressure volume work, because this is expressed in terms of the external pressure, plus now the P delta V term that came from our enthalpy. And you'll notice, because this pressure is our external pressure and this pressure is the system's pressure itself, the internal pressure, they are the same, they're constant. The only difference is their sign, meaning that I could cancel these terms out. They're redundant. So what does that leave us? This leaves us with enthalpy is equal to mcs delta T, or you will sometimes see this as the change in enthalpy of a chemical system is equal to the heat that is exchanged or evolved or transferred as a result of our system being held at constant pressure, so heat at constant pressure. Now, as mentioned in our little kind of lecture plan, this is really where we're going to live when it comes to the idea of thinking about enthalpy. So at constant pressure, the change in enthalpy of some kind of chemical system is exactly equivalent to the heat exchange of that system. So at constant pressure, heat and enthalpy are mathematically equivalent. And sometimes you will even hear me say something like delta H for some kind of chemical system that is a reaction as being known as the heat of reaction. So for example, let's consider the change in enthalpy for various changes of phase for different substances. So let's look at, I don't know, ice melting. So what is happening when ice is melting? So when ice is melting, we are going from solid to liquid water, and we call this process melting. You will also see it as fusion. Talk about that much later. And remember, solids in general, because we have less molecular motion, we've got less thermal energy in general, this is going to be something that is at a lower energy state compared to liquid water, which is a higher energy state. So if I want to take my ice cubes and I want to convert them into liquid water, and we're doing this just kind of like at lab conditions or at home in your kitchen, you know that this is going to require us to take in heat from the surroundings. So if we're taking in heat from surroundings, then that means that we've got a positive sign on heat in our heat transfer. So heat is being transferred into the system. So now that we have warmed our system, or we have heat transferred into the system from the surroundings, we would say that the enthalpy of this process, which is equal to the heat that has been transferred, transformed, etc., into or out of our system, is going to be equal to the amount of heat that was absorbed by the system, and that absorption has that positive sign. Another example would be something like, let's talk about water vapor condensing, so gaseous water. Condensing. So if we've got gaseous water that is being condensed, we are going from a gas phase to a liquid phase. So from steam to liquid water. And we know that gases have an inherent high amount of energy associated with them. They're a high energy phase. We've got a lot of kinetic energy, right? Those molecules are moving a lot higher, or a lot more with a lot higher kinetic energy. And our liquid water, this is a lower energy state. So let's think about what has to happen if I've got steam and I want to condense this into liquid water. In order for this to happen, the heat that is found within this system is going to need to be transferred to the surroundings. In order for this high energy phase to lower energy, it's got to get rid of some thermal energy. So instead of absorbing heat, we are going to see that heat is released by the system. And so the enthalpy of this process is going to be the amount of heat that is released to the surroundings. So the amount of heat that is lost to the surroundings. So up here, this is the amount of heat gained by the system from the surroundings. And here we're looking at the amount of heat lost by the surroundings nope, gained by the surroundings or lost by system. There we go. Amount of heat that's lost by the system to the surroundings. I guess I could probably simplify that. And I think probably these labels are a little bit backwards if you want to think about it in a more conceptual sense. So the heat that is gained by the system, heat that is lost to the surroundings. I guess I effectively just undid what I had going on before. Okay, so big idea here is that at constant pressure, which is going to be the majority of different chemical systems and their changes that we're going to look at in Chem 210, the enthalpy is simply equal to the change in heat. So now that we know that, let's start practicing looking at the change in enthalpy by looking at how heat is transferred at constant pressure for some chemical system. And here we're going to be now moving into the idea of the heat of a reaction, or the enthalpy of a reaction. So remember, we have now said that we're calling this heat, right? Enthalpy and heat are now kind of interchangeable with one another as long as we're at constant pressure, which we're going to be for the rest of the class. So let's get some practice looking at changes in enthalpy, in other words, heat transfer, constant pressure, in our next video.